To introduce Boyang Wang, a tenure-track assistant professor at the University of Cincinnati. He received his PhD from the University of Arizona. And his current research focuses on data security and privacy, adversarial machine learning, encrypted traffic analysis, blockchain and applied cryptography, so lots of stuff. And he's here today to talk to us about fingerprinting encrypted voice traffic on smart speakers. So I will let you take it away.
All right. Well, thank you for the introduction. Welcome to my talk. I'm Boyang. I'm assistant professor from University of Cincinnati. It's a great pleasure to be here. And before I started, I would like to thank Wenhai, Christina, and Jerry again for inviting me here and for providing such a great opportunity to share our recent research. So the title of my talk today is Fingerprinting Encrypted Voice Traffic on Smart Speakers. So basically today I'm going to tell you a story, and at the end of this story you will learn that anyone can learn what you say to a smart speaker. So here a smart speaker means Amazon Echo or a Google Home. So a smart speaker essentially is a voice control device. You can say voice commands to the smart speaker and you can get the corresponding response. Right? For example, you can say, Alexa, what is the weather? Then you can get the weather information from this device, or essentially is corresponding voice services on the cloud. And as of 2019 in the US, we have more than 29% of US households have smart speakers. And the total number of smart speakers we have in the US, this is more than 133 million. And in 2024, the approximate market value for smart speakers is going to increase to $30 billion US. And currently in terms of market share, Amazon Echo has about 70% and Google Home has about 26%. And we do have other smart speakers available on the market, but those two are the two major voice service providers. And you probably will receive one of those during this holiday season as a gift, right? And so in case you don't know how a smart speaker works, so when you say a voice command to a smart speaker, for example, Amazon Echo, and this device will send the audio file of your voice command to the server. Then this server, for example, Amazon Voice Services, have normally two major components. One is called automatic speech recognition, and the other one is called natural language understanding. And for this automatic speech recognition, it will transfer the audio file of your voice command into text. Then based on the text of your voice command or your command, this natural language understanding is going to generate a corresponding response of the audio file, and the server will send the audio file back to your device. So that's why you can hear the corresponding information based on your voice commands. And the traffic between the smart speaker and the cloud server is encrypted with standard encryption algorithms, so for example, AES. So today, the research is based on our recent paper. So this is called Fingerprinting Encrypted Voice Traffic on Smart Speakers with Deep Learning. And this was done by a group of graduate students in my lab, collaboration with a couple of faculty at the University of Cincinnati, and also a collaboration with Dr. Swen from Purdue University as well. So in this paper, we studied this voice command fingerprinting attacks by using deep learning. And based on our results, we believe that this attack can reveal privacy of millions of smart speaker users. So first about this attack model. So here we assume that there is a passive attacker which is between a smart speaker and the cloud server. And this attacker can eavesdrop encrypted traffic between a smart speaker and the cloud server. And normally your smart speaker is connected to a Wi-Fi access point. And then in this case, this passive attacker could be someone on your Wi-Fi network, or a compromised Wi-Fi access point, a compromised router, or even your internet service provider. And the goal of this attack is to infer which voice command you say to a smart speaker. And if an attacker can do this, that means that this attacker can infer what kind of activities you have at home and things you like and things you don't like. And this could lead to an intended disclosure and ultimately could harm internet freedom as well. So essentially, this voice command fingerprinting is a type of encrypted traffic analysis, which have been studied by the research community for many years. The most famous one is called website fingerprinting. And in this website fingerprinting, the goal for this attacker is to infer which websites a user visits in Tor networks, for example. And in addition to that, we have video stream fingerprinting. And in this attack, the goal of this attacker is to infer which YouTube video a user watches over encrypted traffic. And for this voice command fingerprinting, this is relatively new. And there are currently two research papers can be categorized in this direction. So the first one is, this was published in PASS 2019. And in this paper, the authors studied 3 voice commands on Amazon Echo. And for each one, they only had 3 traffic traces per voice command or per class. But the goal of this paper was to try to identify different smart home devices. Okay? And the second paper we have, this was published in CNS 19, and this is actually one of our previous study. So in this paper, we evaluate 100 classes, which means 100 voice commands. But for each one, we only had 10 traffic traces per class. Or in other words, the current study we have limited data sets, which could affect our understanding about the privacy leakage in this voice command fingerprinting. So then you may wonder how this encrypted traffic analysis, this fingerprinting is possible, because although the traffic between a smart speaker and the cloud server is encrypted with standard encryption, for example, AES with TLS 1.2, so that means the attacker cannot decrypt those packages. But on the other hand, this adversary can learn side channel information from the traffic. More specifically, this attacker can learn the size of each packet and can learn the direction of each packet and can also learn the order of those packages as well. And just to give you a very quick example, so here I have 3 heat maps. And for each heat map, I have 10 traffic traces from a same voice command or from a same class. So that means for each one, I repeat the voice command 10 times. Then I get both the incoming and outgoing traffic from the smart speaker. So I list 10 traffic traces here in each heat map. And 2 things we can learn from those 3 figures. So first thing we can learn is that, so if I do have a traffic trace, this is from the same class, then as you can see here, although every single time it is not exactly the same, but it is very similar. And another thing we can learn from those 3 heat maps is that if I do have a traffic trace from a different class, then potentially this is different, right? So for example, if based on those 3 heat maps, so now I give you another traffic trace, and at this point, we don't know the class, right? Or we don't know which voice command it is. So now, based on these 3 heat maps, can you tell me which voice command it is for this traffic trace here at the bottom? Any suggestions? Is it the first one or the second one? Second one, right? So Alexa, what is my sports update, right? So as you can see here, the reason here is that because this, we can see this one has a very similar pattern as the second heat map we have, okay? So from this example, we can tell that it is possible to fingerprint different voice commands based on the traffic pattern. All right. So now let's take a look at another example. So now again I have 3 heat maps, and again in each heat map I have 10 traffic traces for one voice command. And for each traffic trace I have both outgoing and incoming traffic. So on the first one I have Alexa, what is the price of Bitcoin? Alexa, second one, Alexa, what is my traffic report? And third one, Alexa, what is the weather? So now based on those 3 heat maps, now if I have another traffic trace here, okay, and can you tell me, based on those 3 heat maps, can you tell me which voice command or which class it is for this traffic trace at the bottom here? So how many of you think this is the first voice command here? Okay, 1, okay, good. 2, all right. So how many of you think, or 3, so how many of you think this is the second voice command here? All right, good. And how many of you think this is actually the third voice command? Okay, good, good. So actually this is another voice command. Alexa, what is gluten? All right, so as you can see from this example, right, although from the previous slide we know that this is possible to fingerprint voice commands based on traffic pattern, but as you can see from this example, this is not very easy to do by humans, right? So in this paper, next let's talk about the assumptions we have in this study. First, we assume that this is closed word setting, so which means we assume that the attacker knows a set of commands, for example, 100 voice commands. Then a traffic trace that is captured from a target is definitely associated with one voice command in this set. Okay, that's the assumption. This is called closed word setting. And in addition to that, we assume attacker knows the start time and end time of each traffic trace. And also attacker knows the IP address of a smart speaker. And attacker has the same type of smart speaker as the target, as the user. And each traffic trace includes both the packages for voice command and also the packages for the corresponding response as well, which means we have both outgoing traffic and also the incoming traffic from the server, right? Then essentially, this problem can be formulated as a supervised learning problem, which means attacker has an unlabeled traffic trace, which is captured from a target. Then this attacker can collect training traffic traces based on each voice command in this set. Then this attacker can decide which label or which class it is for this unlabeled traffic trace from this target. Okay? But one of the main challenges we have here is that we do not have large-scale research data sets to evaluate the privacy leakage in this kind of problem here. Then here are the main contributions we have. So in this study, we develop an automatic traffic crawler. And by using that, we collect 2 large-scale data sets on Amazon Echo and Google Home as well. Then we leverage deep learning to advance the attack accuracy. More specifically, we leverage convolutional neural networks, long short-term memory, and also stacked autoencoder as well. And based on our results in the closed word setting, for CNN, for example, we can achieve 89% of accuracy, which is very impressive. So first, let's talk about the traffic crawler we have here. So as you can see from this figure, so for this traffic crawler, we have 3 major components. First, we have this Raspberry Pi served as a Wi-Fi access point. Then we have a smart speaker. Here we have Amazon Echo, 2nd generation, which is connected to this Raspberry Pi wirelessly. Then we have a regular speaker, which is connected to this Raspberry Pi using USB. And this Raspberry Pi is connected to the internet using an Ethernet cable. Then on this Raspberry Pi, We generate audio files for different voice commands by using public text-to-speech APIs from Google and Amazon. So for each voice command, we generate 5 different audio files, one for each different automated voice we have. And overall, we have 3 female voices and 2 male voices. Then we play those audio files one by one. And when we play one audio file, we wait a little bit in order to get the response from the server. In the meantime, we run TCP dump to collect the encrypted traffic to the server and also from the server as well. And by doing this, by using this automatic traffic crawler, we can collect 3,000 traffic traces each day without any human interaction. And by using this, we collect 2 large-scale data sets. So the first one is on Amazon Echo. So as I mentioned, for each one, we have 100 voice commands or 100 classes. And for each voice command, we have 1,500 traffic traces. And for those voice commands, we actually selected based on Amazon Echo weekly emails. So if you do have Amazon Echo at home, you can receive weekly emails from Amazon. And for each email, it will tell you what are the popular voice commands people will ask during that week. Right? So that's how we select those popular voice commands. And for Google Home, we also selected 100 voice commands as well. And for the data collection, for Amazon Echo dataset, it took about 9 weeks to complete. And the size of the entire data set is about 25 gigabytes. And similarly, for Google Home, it took about 9 weeks to complete as well. And the data collection started in March 2019, and we completed that data collection in August 2019. Then for the attack, we leverage 3 deep learning models. First one, convolutional neural networks. The reason that we select CNN is because, in general, CNN is pretty good in terms of classification, especially for images. And that's why we think CNN is potentially a good solution for this fingerprinting attack. And in addition to that, we also leverage long short-term memory. And long short-term memory is very good in terms of handling time series data. And for traffic traces we have, essentially those are time series data. So that's why we think LSTM here is potentially a good option for this attack. And we also leverage stacked autoencoder. And stacked autoencoder is very good in terms of extracting features from high-dimensional data. And for the traffic traces we have a lot of packages, or in other words, we have a lot of dimensions. So that's why we think this stacked autoencoder is potentially a good option for our problem as well. So here is a brief overview of the framework for our CNN model. So as you can see here, we have 1 input layer, and overall we have 4 convolutional layers for max pooling, 1 global pooling, 1 dense layer, and 1 output layer at the very end. So we did try several different structures, and this one was the best we got in terms of attack accuracy. Then for LSTM, so we have, as you can see here, we have 1 input layer, overall 5 LSTM layers. After each LSTM layer, we also have dropout. And at the very end, we have 1 dense layer and 1 output layer as well. So for each LSTM layer, it has multiple LSTM units. Normally it's about 128 or 256. And for each unit, we have forgot gate, input gate, and also output gate. So those are the standard structure for LSTM unit. And for LSTM, we also try several different structures as well. And this is a framework for our SAE. And we have 4 layers for the encoder, 1 layer for the code, and 4 layers for the decoder. And during the training, we train the encoder, code, and decoder. Then during the classification, we take the encoder and code out. Then we add an additional dense layer at the very end for the classifier. And in addition to those three neural networks, we also leverage this ensemble learning. And the basic idea is to make multiple models to vote during the prediction so that we can achieve a higher accuracy. And so basically we take the last layer of each single model, and then we assign a weight for each one. We calculate the prediction overall. And we have average ensemble, which means the weight for each single model is the same. And we have also this weighted ensemble as well, which means the weight for each model is based on the performance of each single model. Okay. And so next, let's talk about the data format. So after we collect those raw traffic data, we represent those data into two different formats. One is binary, which means we only keep the direction information for each packet. And then the other format, we call it numerical format, which means we keep both the direction and also the size of each packet. So that means, for example, if I have a traffic trace, has 4 packages. First one I have 500 bytes, and this possible one is outgoing. And second one I have 200 bytes outgoing as well. Third one 150 bytes incoming, and the last one is 300 bytes outgoing as well. And if this is binary, then I represent it as +1, +1, -1, and +1, right? Direction only. And if this is numeric, then we have +500, +200, -150, and also +300 as well. Okay? And for traffic traces that are from different classes or from different voice commands, we actually padded them or trace them to the same length before we feed into neural networks. Because for neural networks, we have to have the same length for data from different classes. Then for the experiment setting, so we implement our attacks with Python, and we use Keras as the front end and TensorFlow as the back end. And we used GPU for the training, and we did 5-fold cross-validation. And for the training, we have 64% of the data, and 16% of the data for validation, and 20% of the data for test. And for each single model, we searched hyperparameters by using this NNI, which is a Microsoft toolkit. And we use this TPE as a tuning algorithm, which is available from this NNI. And for each single model, we run 50 iterations with this NNI, or we stop if it is longer than 200 hours, which is about roughly 9 days. Then, so after we search those hyperparameters, so those are the results we got in this closed world setting on this Amazon Echo dataset by using both outgoing traffic and also incoming traffic. So as you can see from this table, the first thing we can observe here is that numerical format actually leaks more information, which means with the same model, if attacker uses numerical format, then potentially it can achieve a higher accuracy. And the second thing we can learn from this table here is that both CNN and LSTM, they have a very similar accuracy, and they are both better than SAE in our results. And in addition to that, we learned that Ensemble Learning can improve the attack accuracy. For example, for CNN, with the numerical format, we can achieve 89% of accuracy. But by using weighted ensemble, we can further improve the accuracy to 92.8%. Okay. Any questions at this point? All right, good. So those are the results we got on Amazon Echo dataset by using, again, outgoing and incoming traffic both. And we also evaluate the attack accuracy on Google Home dataset as well. And basically, we have very similar observations compared to the results we had based on Amazon Echo dataset. So, which means, again, the numerical format can achieve a higher accuracy. And both CNN and LSTM, they have very similar performance here. And they're both better than SAE. And for this Google Home dataset, we did not evaluate the Ensemble Learning because CNN already achieved a very high accuracy. Besides the variance we got from those five-fold cross-validation was very low, so we did not test Ensemble Learning for this dataset. And then next, we compared our neural networks with a couple of attacks based on traditional machine learning algorithms. So the first one is called Cumul, and this is based on the cumulative function of traffic size by using SVM as the classifier. And the second one, which is CNS19, this was one of our previous study. And in this one, we used a set of manually selected features and by using AdaBoost as a classifier. So in this comparison, as you can see here, both our CNN and LSTM can achieve a better accuracy than Cumul and CNS19 here. And CNS19 can actually achieve a better performance than Cumul. And for each attack here, as you can see, that attack accuracy is very high compared to random guessing, which is only 1%. Okay? And another thing we observe from this result here is that in general, for neural networks, they require more time in terms of training compared to attack methods that are based on traditional machine learning algorithms. And this result is based on closed word setting by using both incoming and outgoing traffic based on numerical format here on Amazon Echo dataset. And next, we also evaluate the impact of datasets. So again, we compare those 5 different attacks, but we change the size of the dataset. Each single time, we still have 100 voice commands or 100 classes, but we keep increasing the number of traces for each class. All right. So as you can see in this figure, at the very beginning, when the number of traffic traces is 100, and in that case, actually, CNS19 is the best attack method. But when more data are available, then both CNN and LSTM can perform other attack methods here. And this is based on Amazon Echo datasets by using numerical format here, using both outgoing and incoming traffic. Right. So now, however, a key question here is: are our attacks practical on human voices? Okay. So because during our data collection, also we leveraged 5 automated voices by using public text-to-speech APIs, which means we can offer a certain level of variances in voice commands, but it's not enough because we know that for human voices vary a lot due to many factors, for example, age, gender, and accent. And that means this could potentially lead to high variances in voice commands and potentially affect the traffic pattern of outgoing traffic on a smart speaker. And in addition to that, we know that humans can ask the same intent with different tags. Right? So for example, Alex can ask, is it going to rain tomorrow? And Bob can ask, will it rain tomorrow? And both of the voice commands, they have the same intent, but they have very different tags here. And this, again, could potentially lead high variances in voice commands and affect outgoing traffic, the pattern of outgoing traffic on a smart speaker. Okay? Then apparently evaluating all the possible variances by considering both human voices and tags is nearly an impossible task. But on the other hand, we observe that for those variances caused by human voices and tags, they do not affect the responses generated by the AI-based voice services on the server side. And based on that observation, we believe that if we only evaluate the attack accuracy of our models by using incoming traffic only, then we can demonstrate that our attacks are actually practical, even though we could have high variances in human voices. Right, so here are the results we got. So as you can see here, even by considering incoming traffic only, our attack models can still achieve very high accuracy. So for example, originally if we use both incoming and outgoing traffic, LSTM, for example, can achieve 88% of accuracy. But now if we use incoming traffic only with LSTM, we can still achieve 85% of accuracy. And similarly for weighted ensemble, previously we can achieve 92% of accuracy by using both incoming and outgoing. So now if we use incoming traffic only, we can still achieve 86% of accuracy here by using weighted ensemble. And we got similar observations on Google Home dataset as well. And by doing this, we actually demonstrate that our attacks are practical on human voices. And those results are based on modeling echo data sets in closed word setting based on numerical format here. Okay. And then for modeling echo data sets, based on because now we use incoming traffic only, and based on the responses we got from each voice command, we further categorize those voice commands into 3 different groups. So first one we call it single response commands. So that means during our data collection, if we ask this voice command every single time, we got the same or very similar response from the server. So for example, if you ask Alexa, where's Mount Rushmore, then every single time you got almost the same response from the server. And the second type here, we call it time sensitive, which means when we ask this voice command here, we got different content, but the format is very similar. And this could change based on the time here. For example, if you ask Alexa, what is the weather, then the information from yesterday and today could be very different. And the last category we have here, we call it multiple response commands. So which means when we ask one voice command here, we could potentially receive several different responses. So for example, if you ask Alexa, tell me a joke, and every single time you could potentially get a different joke, but overall there are only 6 or 7 different jokes. Okay, so if you try 100 times, then you will always have those 6 or 7 jokes. Then based on this, we evaluate the attack accuracy based on each category. So as you can see here, for single response commands and time-sensitive commands, those are relatively easier to infer because the content or the format of those responses are very similar. And on the other hand, for multiple response commands, those are not that easy to infer, but still we got pretty good accuracy here with 70% of accuracy using CNN model. And so this is based on Amazon Echo dataset by using numerical format and incoming traffic only. So one thing we can learn from here is that potentially if voice service providers, they could increase variances in terms of tags of those responses, then this could potentially mitigate the privacy leakage for users to some extent, but not a lot. Okay. And then next, we also evaluate the open world setting for our attacks. So in this open world setting, we assume that attacker, again, knows a set of commands. And then for a traffic trace that is captured from a target, the voice command of this traffic trace may not be in this set here. And essentially, for this open world setting, this can be formulated as a binary classification problem. And in order to evaluate the performance in this open world setting, so we have one monitored list. And in this one monitor list, we have all the 100 voice commands we have in the closed world setting. And for each voice command, we took 200 traffic traces for each class. Then we have another unmonitored list. And this monitor list has another 100 different voice commands. And for each one, we collected 200 traffic traces for each voice command. Then we retrain the model. So here are the results we got in this open world setting. So as you can see here, based on this numerical format and also incoming traffic only, our attacks are very effective in terms of deciding whether this traffic trace is in this set or not. Right? So for example, for CNN, we can achieve more than 99% of accuracy and more than 99% of a true positive rate here. And the false positive rate is also very low. And this is the same for every single model we have. Then based on all those results from the attack, now we want to propose a defense in order to mitigate the potential privacy leakage for users. So this defense we have here, the basic idea is to obfuscate traffic pattern by integrating two existing methods. So the first one here, this is called adaptive padding. And the basic idea is to add dummy packages in the traffic trace. And the second one here, this is called differential privacy. And the basic idea here is to change the package size of each packet based on the size of its previous packages. And for our defense evaluation, so basically we applied this proposed defense on both outgoing and incoming traffic. And since we cannot change the current protocol on smart speakers, so our results are simulation-based, which means the obfuscated traffic are generated based on the original traffic in our datasets. And during our evaluation, we evaluated two scenarios. So the first one is we assume that attacker trains those neural networks with the original traffic or with no defense. Then test with obfuscated traffic when defense is available. And the second scenario here is that we assume attacker trains with obfuscated traffic and also tests with obfuscated traffic as well. And between those two, the second one is a more realistic setting because we assume that attacker can adapt when a defense is available in practice. And so those are the results we have, as you can see from this table. So with for the first scenario here, if attacker trains with original traffic but tests with obfuscated traffic, then our defense can reduce the attack accuracy to almost 1%, which is very close to random guessing. and this is effective for different attack methods as well. And in addition to that, if we assume that the attacker can train with obfuscated traffic and test with obfuscated traffic, then our defense can still reduce the attack accuracy to 28%. And this is compared to 89% with Ensemble Learning by using incoming traffic only. And as you can see from this table, our defense is also effective against the other two attack methods, which are based on traditional machine learning algorithms. And next, another thing we did was to evaluate the impact of this privacy parameter epsilon in differential privacy. And this is based on Amazon Echo dataset by using both incoming and outgoing traffic in numerical format. And so as we can see here, for a smaller voice, a smaller privacy parameter epsilon here, that means a higher noise level for differential privacy. That means our defense is more effective in that case. But on the other hand, if we have a greater value of privacy parameter, that means the noise level is lower, the defense is less effective in that case. Okay? And also we evaluate the potential trade-offs we have for this defense here. And overall, our observation here is that our defense only introduces low latency and affordable bandwidth. So for example, if the privacy parameter or the privacy budget epsilon is 0.005 and the latency of each traffic trace on average, this is about 136 milliseconds, which is very low. And then the bandwidth in that case overhead is going to be about 55 kilobytes. And if we increase the privacy parameter epsilon here, we can reduce the latency of each traffic trace, but we have to increase the bandwidth overhead in this case. So there is a trade-off here. Then about the limitations of our study. So the first thing about the selection of voice commands. So we evaluate 100 popular voice commands in our study on Amazon Echo and also Google Home. But on the other hand, we do realize that the number of voice commands people could ask in practice is much greater than this number here. And it's going to be very interesting to see how we can evaluate the privacy leakage of voice command fingerprinting with a larger scale of voice commands. And in addition to that, for the voice commands, we did not select voice commands that are involved with interactions with another IoT device or any credit card transactions. So for example, if we ask Alexa to order 1,500 pizzas, we don't have the money, and second, we cannot eat 1,500 pizzas. And another limitation here is that so in our evaluation, we assume that each voice command, it has the same priori probability here. But this is actually not the case in practice, especially when we consider particular context here. So for example, let's assume that we do capture one traffic trace from a target. And based on our models, we think that this is either the first class, how many days until Christmas, or the second class, how many days until tax day. And since we captured this traffic today, and this is still before Christmas, and obviously the probability of the first class is higher than the probability of the second class. Right, so those things we did not consider in our evaluation. And that's the end of my talk. Any questions? Yes.
So in this case, like you had that automatic crawler setup, right? The Raspberry Pi. And
Yes.
yeah. So, but some currently like Amazon like offers like Alexa Skills Kit where you can make those queries like at a faster scale, like using their API calls itself. Is that something you considered, and is that not like helping in this case, or would that help to scale this?
So the question here is, can we also, let's say, fingerprint different voice skills? Is that
Like there's API calls you can make rather than like having an actual speaker. You can make those calls directly like through like code, right? So
okay?
so in this case, like, is there anything like inherently like vulnerable with the speaker that you're exploiting, or is it how is it different like from making like asking Alexa on my phone for the same thing? Can the trace like sniffing be done in that case also? Like if I were to ask Alexa from my phone.
Oh, so you're saying, let's say if we use the Alexa app on the smartphone, and can this type of attack figure out fingerprint what kind of voice command? I would say potentially yes. If attacker has exactly the same setting as you have, then it's possible. I would say, yeah. But again, the whole assumption here, as you can see here, is we assume that the attacker can have a very similar setting as a target, so that you can, because if you change a device and you change the network setting, the traffic trace or the traffic pattern could be very different, although it is the same voice command. In that case, the attacker has to recollect the data in that case, or potentially leverage other techniques, for example, transfer learning, to infer which kind of voice command it is. I would say it's possible, but there are additional things where data collection need to be done in that case. Yeah, that's a very good question. Any other questions you may have?
Okay, if we don't have any more, let's thank our speaker.
Well, thank you so much.